Welcome back, everyone. In this lecture, we're going to show you how you can use Python code to create autoencoders for the purpose of dimensionality reduction. We can use an autoencoder for dimensionality reduction by separating out the autoencoder into two parts, the encoder and the decoder. So here we have the full autoencoder. Recall the autoencoder, the main idea is that we have the same number of inputs as we do outputs. And then inside of the autoencoder, we do a dimensionality reduction and then expand it back out. So what we end up doing is we separate this out into two parts, an encoder and a decoder, where the idea of the encoder is to take something that's highly dimensional and then encode it into a lower dimensional space. And basically the decoder job is to expand back out that low dimensionality in order to make sure that that hidden layer in the middle of the autoencoder is actually learning correctly what features are important. Because if it's not able to learn correctly what combination of features is important, then you're going to have a really poor output. So that's the job of the decoder. So what we do is we train this all together until the hidden layer becomes really good at extracting useful information, and then the decoder can expand that back out. Once we've trained the full autoencoder, then we just grab the encoder section, and now we have something that can successfully reduce dimensionality. So we train them together, but when we actually want to use it for dimensionality reduction, we only need to grab the encoder part. So this encoder can now successfully reduce dimensionality of the original data by taking combinations of the original features. Now you may be asking, what use cases does this actually have? Dimensionality reduction has a wide variety of use cases. It can be used for things like compressing your data set, visualizing data in lower dimensions, and most importantly, revealing hidden relationships that are not clearly seen in higher dimensions. When we're dealing with feature data that goes beyond 3 dimensions, then it becomes very difficult to actually visualize this and understand the relationship, especially if you're performing something like a classification tasks. It may be quite useful to understand just how separated are these classes. And if you're able to visualize this, either in 3D or 2D, you may be able to get an understanding of just how separable these classes are. So for example, here we have an example of dimensionality reduction where we're starting from 3 dimensions. We can see here that these two clusters are highly separable, and we're actually able to visualize 3 dimensions. But you can imagine that this could have been a case where we have 11 dimensions, and so there's no way of actually visualizing the classes themselves or all the features at once. So what we could do is reduce that dimensions into either 2D space or 1D space or 3D space for operating from something much higher, and then see if we're actually able to separate those classes or not, just to get some intuition of how separable these two groups are. Okay, so let's actually code out this exact problem set, and we're going to hop over to a notebook and get started. All right, here I am at a notebook. I've already imported NumPy, Pandas, Seaborn, and Matplotlib, and I'm going to do one more import that we actually haven't seen before, which is from sklearn.datasets import make_blobs, which is a really useful function for just quickly creating a data set. So we're going to be just creating a data set so you can get an idea of how an autoencoder can be used for reduced dimensionality. And then later on in your exercise, you'll work with a real data set to actually apply this. So let's create a data set with this makeBlobs function. And we're going to call makeBlobs. And if you want to explore makeBlobs in more detail, you can do Shift-Tab here and see the various functionality that is available for it. But what we're going to do is just walk you through the main parameters we're going to be passing in. First, we're going to decide the n samples, which is essentially how many rows do you want in your data set. So in this case, we'll ask for 300 rows, and then we'll say n features, and this is where you can decide how many features you actually want. So I'm just going to create at first 2 features for this data set, and then we can decide on centers, so how many clusters do you actually want. In this case, I want 2, so we can think of this as a kind of binary data set belonging to one of 2 clusters. And then finally, we can say cluster underscore standard deviation, essentially how much noise is there for these clusters. And we'll set that to just 1.0. And then to make sure you get the exact same data set that I do, go ahead and set your random state to 101, because this is essentially going to make 300 samples part of 2 clusters with just 2 features. We go ahead and run that, and then we can separate out our data, because if we take a look at this data object, it's a tuple of 2 arrays. where the first item is these X features, and then the second item is your actual labels. So we take a look at this. By this tuple unpacking, we have this X feature data, and then if we take a look at Y, we have their actual corresponding labels, either belonging to cluster 0 or cluster 1. Remember that in this case, we're not actually worrying about any sort of classification. Instead, we're going to see how to reduce the number of dimensions here. You'll notice that I only created a 2-dimensional data set. What I'm going to do is add a third feature that is just noise. So we're going to say np, let's go ahead and put this in a new cell, np random.seed, and go ahead and set your seed to 101. And in the exact same cell, so you get the same noise I do, create z noise and say np random normal, and say the size is equal to the length of x. And then say z noise and convert that noise array into a series. So all I did here is with these 3 lines, I now have this series, which is just a bunch of random noise for every single row from 0 to 299. What I'm going to do next is create a data frame called features by saying pd data frame on x. So if I take a look at my features right now, I have 0 and 1, which is the original features created by make blobs. These 2 features actually have some sort of correlation or effect to separating out all these data points into their respective clusters. What I'm going to do is say features is equal to pd, and I'm going to concatenate my original features with that noisy series. And then we'll say concatenate this along axis is equal to 1. And let's go ahead and just relabel those columns to be equal to some x1, x2, and then x3. So what does this actually look like? I say feature head, and I see x1, x2, and x3. And I can actually perform a scatter plot here by saying plt scatter. And let's go ahead and scatter plot x1 versus features x2. Recall these are our original features, so they should be informative. So here I see the 2 clusters. There's clear separation here, and we can actually specify what to color them by saying c is equal to y, which means just color them by the 0s and 1s. So clearly, in my original data, I have these very clearly separated clusters. What I can do is I can now actually visualize this in 3 dimensions by, again, visualizing the extra noise we added in as our third made-up feature. So we can say from mpl underscore toolkits dot mplot 3D import axes 3D. Okay, so we have MPL toolkits, mplot 3D, import axes 3D, and then I'm going to create a 3-dimensional figure by saying fig is equal to plt figure, and I'm actually then going to say axes is equal to fig add underscore subplot. And you can check out our Autoencoder notebook. So if you actually go to the Autoencoder's notebook that this lecture is based upon, you scroll down here, I've linked for you the actual information from the online documentation. So don't think that I have this scatter plot memorized. Instead, I just went ahead and referenced that link. So keep that in mind. That's how I know this code. And we're going to say add subplot 111. And then most importantly, we say projection is 3D. And then I'm going to call a scatter plot here. Ax.scatter, and we'll say scatter feature x1 against feature x2 against feature x3. And then we'll go ahead and color that by the correct labels again. So I run that, and I see this nice 3-dimensional scatter. Now what's really cool is if you're operating in the latest version of Jupyter, you should be able to say %, matplotlib space notebook, run that cell, and then rerun the plotting. And you should see that this is now an interactive plot that you can explore. So notice here, along this 3rd dimension that we created, here this kind of noisy one along the z-axis, that is actually just straight noise. What we originally saw was the scatter that looked like this. So if we looked at it straight on top, notice that we have these tight clusters, but this third dimension is kind of adding a lot of noise that actually does not separate out purple versus yellow. There's no separation between purple versus yellow in this third dimension of noise that we created. There's clear separation of purple versus yellow along these two original features. So what we're going to explore is if we can create an autoencoder that can essentially try to filter out which features are important and which are not. And we would assume that it'll take information from x1 and x2, and it won't take information from x3, since x3 really does nothing to tell us about these two blobs, since it's just noise. Okay, so if you want to kind of turn off this plot, you can just come up here and then click this little off button. I'm zoomed in so you can't see the whole thing, but here we have now those two clusters, x1 and x2, informative features, x3, essentially just noise. It shouldn't be very informative, especially for informing you on how separable these classes are. So now let's explore creating an encoder and decoder. I'm going to come back down here, and we'll say from TensorFlow.keras.models, import sequential, and then from TensorFlow.keras.layers, import dense. And then lastly, what I want to show here is we're actually going to import stochastic gradient descent as our optimizer. And one way we can do that is saying from TensorFlow.keras.optimizers, import SGD. And what's nice about stochastic gradient descent is you can play a lot with the learning rate of the stochastic gradient descent to try to help out your autoencoder. Now, in our particular case, this is a very simple data set, so affecting the learning rate shouldn't really make much of a difference. But it's quite common in autoencoders to use something like stochastic gradient descent and then play around with that learning rate and make it a little slower if you notice that hidden layer is having trouble understanding what features are important. So how do we actually do this? What we're going to do is we're going to create an autoencoder that starts off with the 3 inputs, reduces it down to 2 neurons in the hidden layer, and then expands it back out to 3 neurons. So we want to make sure that the input 3 matches the output. And we're going to do this in 2 steps. We'll first create an encoder, and we define this as its own separate model by saying encoder is equal to sequential, and saying encoder add, and we add in a dense layer, and we'll say units is equal to 2. We'll specify the activation function to be a rectified linear unit, and most importantly, we need to specify that our input shape is equal to the original input shape, which was 3. So we're going from 3 as our input down to 2 dense units. So that's our encoder, and then we need to match a decoder to it. So the decoder is going to be equal to, again, its own sequential model, and then we'll say decoder is equal to, decoder add, and then we'll add dense layers. And in this case, the decoder ends with 3 units. Go ahead and use the same activation function, a rectified linear unit, but its input shape is coming from the output of this encoder. So we're going from 3 to 2, and then the input shape is going to be equal to that 2, and then it's going to come out as 3. So that's what's happening here between the encoder and the decoder. We start off with 3 features, go down to 2, and then from that 2, as the input for the decoder, we expand back out to 3. So very simple autoencoder here. To define the actual autoencoder, we'll say it's simply a sequential model, and this is what's really nice about the Keras syntax, is we just pass in a list of encoder and decoder, and we've essentially combined them together. So what we're going to do is we'll train the autoencoder together. That way, we can have the encoder learn the best way to reduce from 3 to 2 in order to reproduce on the decoder side a similar output. And then once the autoencoder has learned this, we'll separate out the encoder section of it in order to just go from 3 to 2. So the last thing we need to do is compile our autoencoder. So we'll say autoencoder compile, and we'll go ahead and say our loss is mean squared error, since these are all continuous values. And here's where you can play around with the optimizer. If you really wanted to, you could just pass in the string code atom, But typically, what's really nice is to play around with stochastic gradient descent and then play around with your learning rates. So here we'll just pass in 1.5. Okay, so we have our autoencoder completely set up. Last we need to do is actually scale our data set. We'll say from sklearn preprocessing, just as we've done before, import a min-max scaler. And notice what I'm going to do here is, since there's technically no right answer as far as how you should reduce this dimensionality, I'm just going to fit and transform on my entire data set. Because I don't really have a right answer to compare this to. It's not like I have a correct version of this data set in 2 dimensions. So we'll go ahead and say min-max scalar, and then say our scaled data is equal to scalar, and here I'll just call fit transform on my entire feature data set. So this is what's making this so far different from the supervised learning process, because there was no train test split here, because it doesn't really make sense. We're doing something where we don't actually know the correct answer. We're going from 3 dimensions down to 2 dimensions. Okay, finally, let's go ahead and take our autoencoder, and we're going to fit this, and we're going to take our scale data, and then pass in our scale data as well. This is both x and y here, really. And then we'll go ahead and train this for 5 epochs. This should be pretty fast because it's a very simple data set. Okay, there we go, just kind of a few microseconds per epoch. And then what we're going to do is we'll say the encoded 2-dimensional version is equal to, and notice here, I'm just going to grab the encoder, not the full autoencoder. So just the encoder section, which goes from 3 to 2, and I'll ask it to predict based off my scaled data. Run that, and now if we check out encoded 2-dimensional, run this, and you should notice some behavior that looks something like this. So if we check out the shape of this, it's taken from 300 to 3. So if we take a look at the original scaled data shape, it's 300 rows by 3 features, and we have successfully reduced that down to just 2 dimensions. So let's see what that actually looks like. I'm going to call plt scatter, and we'll call encoded 2 dimensions, and say grab all the rows from the first column and plot them against encoded 2 dimensions, all the rows in the second column. We go ahead and run that, and you should see something that maybe looks something like this. It may not be so noisy here. You may actually just see 2 straight lines. But note that we have this little group cluster and then kind of these points up above here. Now the question is, how well did this actually do at separating out the classes that we know to be the underlying truth? Well, what I can do is I'm going to turn this off here and say C is equal to Y and actually color these. Run that, and you notice that it was able to separate this out, and it got some of the noise here, but it reduced it back down to 2 dimensions where all the yellow points are down here and all the purple points are up here. So why would this be useful in a real-world situation? Well, in a real-world situation, you're dealing with high-dimensional data. So it may not just be 3 features, but it may be something like 11 features, something that's just impossible to visualize, as we did before. So up here, when we actually visualized the 2 3-dimensional clusters that we did up here, we are pretty lucky. We can actually visualize this, and there's no real need for dimensionality reduction. Well, the purpose of this was just to show you that we're going from 3 down to 2. But in a real-world situation, you're going to be dealing with an extremely high-dimensional data set, something that's 4, 5, 6, 10, etc. Something that's just impossible to visualize. So what you would then do is train your autoencoder to go from something like 10 dimensions down to 3 dimensions. And then you'd be able to plot this out in a 3-dimensional space. And you can imagine that if you plotted it out in a 3-dimensional space and saw clear separation by class, because maybe you just wanted to explore the data and see how intermingled these classes were in just general sense, and you saw that there was clear separation, then you would know that these 2 classes are very distinct. If after reducing it down to 3 dimensions or 2 dimensions, there was a lot of crossover between these 2 classes or multiple classes, then you would know which classes are really similar to each other and which classes are very separable from each other. So this is just to reveal hidden insights visually that you wouldn't be able to see before. And your exercise is really going to focus on that. And your exercise will give you a real data set that has 17 dimensions and it'll be your job to actually reduce it down to either 3 dimensions or 2 dimensions and see what components or what categories are highly separable from the other ones. Okay, so again, all we did here is we created an autoencoder by separately creating our encoder first and then our decoder. Coming up next, we're going to analyze how we can perform this same process, but on even higher dimensional data, such as image data. Recall a 28 by 28 image is going to have 784 feature points or 784 pixels or dimensions. So we're going to reduce that down. Okay, if you have any questions, feel free to post to the Q&A forums. Thanks, and I'll see you at the next lecture.